Welcome to Hot Chips 2024. Tutorial 2. The cooling of hot chips.
Hi, everyone. Welcome to the afternoon session. My name is Seshu, and I'm going to chair this session on thermal technology. We all know that the AI revolution is creating all sorts of opportunities in the industry for various aspects of what it takes to deliver generative AI. And one of the areas that is actually seeing a lot of activity and innovation is thermal. So we've decided to dedicate this afternoon tutorial to hear from industry experts about the new techniques that are emerging in this area. And believe it or not, it's not just large companies that are innovating new thermal techniques. There's even a lot of startup activity in thermal nowadays. So as some of my compatriots tell me, thermal has become sexy again. So we're also going to hear from startups this afternoon. So we have a very impressive slate of speakers. We've got people from industry as well as startups, both from companies that are involved in cloud computing and also edge computing. So we should get a pretty broad spectrum of perspectives from our speakers. So with that said, let's start with the first speaker. The first speaker is Tom Garvens. He's the Vice President of Hardware Solutions at Supermicro. And he's responsible for incubating new technologies and offerings for all his lead customers. He's a very hands-on technology executive with over 30 years of engineering leadership in architecture and definition, execution, and launch success. Prior to Supermicro, Tom was the VP of Platform Engineering at Google, where he led the architecture, design, and validation of Google's data center IT systems, spanning servers, GPUs, TPUs, storage, networking, and rack architecture. Before Google, Tom held multiple leadership positions at Dell's Enterprise Engineering Group, spanning PowerEdge, cloud, and CTO organizations. So we are very happy to have somebody with the depth of experience and knowledge of Tom to lead off this session talking about thermal challenges in data centers. Tom? Tom, the floor is yours.
All ready for me? Thanks, Seshu. Appreciate it. Good afternoon, everyone. Proud to be here today. Glad you could be here to attend in person as well. I have a personal philosophy, which is every day be a teacher, every day be a student. There's always something that I think each of us can share with others for experiences they may not have, but also I'm here to learn today as well. I'm here to learn from you. I'm here to learn from the other talks, and so hopefully it's beneficial for everyone. So today what I'm here to talk about, unfortunately, hey guys, presentation isn't up here. There we got it. So today what I'm here to talk about, the agenda. So first off, talk a little bit about context, about kind of what brought us to where we are today and why we're being challenged. And, the generative AI, large language model explosion that happened, a little under 2 years ago now. Going to talk a little bit about data center power and cooling challenges. Talk a lot about cooling today, but we're going to talk a lot about power as well in terms of what the benefits are and the challenges are. And how those things are being addressed. And then lastly, just a little teaser for the future, some things to think about. So to start with, the generative AI large language model era that we're in. Really, for me, it was, I guess, November of 22 when ChatGPT hit the market and kind of took the world by storm. And talking about large language models, changing doubling every 5 years, doubling every 10 years, depending on who you talk to, you get different answers. But today, we're in the trillions of parameters and trillions of tokens, the largest models that are out there. And if you look over to the left, LLM parameters, what are they? To use a simple, kind of parallel to it, it's like a machine. And the more parameters you have, they're like fine-tuning knobs on that machine. And the more fine-tuning knobs you have, the more precise you can make that output. To be honest, a 7 trillion parameter model versus a 7 billion parameter model, you can train both of them. But when you give it a prompt, you likely will get very different output in richness, in accuracy, and in content accuracy. So it makes a big difference as to the size. And then data sets. It's all about data. If you don't have data, there's nothing to train. So it's all about who has large sets of data that then can be trained to actually create an engine so that you hear the term AI factories. Well, how is this an AI factory? Well, a factory is something that produces something new that you didn't have before. That's what generative AI is. It is producing intelligence from what you started with. So it actually is coming up with things that are new. And then as a result of that, just massive GPU compute is required. Well, why is that required? If you think of the size of these models and the sizes of these data sets, basically that somehow needs to make it into a computer. And that data gets stored, in storage and memory. So those ultra-large models need to be sliced up into smaller pieces so they fit in individual memory within today GPU servers. Typical GPU server today has 8 GPUs from a few different vendors and 2 host CPUs that bring in a lot of the control side. And just as an example, so GPT-3 is kind of old today. We've moved past it multiple generations, but just the example, 1,000 A100 GPUs. We're now well into Nvidia's H family. But if you look at that, all clustered together into one large homogeneous computer, it still took 34 days. So when you talk about these batch training runs, yeah, small models can happen in one system and you can maybe get it done in hours. These large ones take a data center. And this is a data center of racks of GPU servers clustered together, acting homogeneously as one computer. And that's one of the big paradigm shifts here. If you read articles about, I've got this large cluster and it was really tough to get it going, but then once it's going, it doesn't stay up because, things are failing on it. That's why I need to snapshot it every few hours. There's so much complexity in these clusters and putting them together. So the rise of the GPU. Many of you here probably know, we've been in a CPU world for a long time. We've been in a GPU world for, maybe 13 years now, where people took servers and they were just stuffing graphics cards in them, trying to do, oil and gas geomodeling. So the GPU kind of emerged first in that traditional HPC space. And back then, CPUs were maybe 150 watts. Now, CPUs are 500 watts. Depending on what roadmap you've seen, you can see GPU roadmaps going up well into the multiple thousands of watts. And the thing that's challenging that is that not only are the temperatures going up, but the temperature that we need to hold the chip to is going down. So we have two things working against us. Thermal densities, as we're going from 5 nanometer to 3 nanometer, how much power and the hot spotting on the chips become critical to deal with. And then just getting a data center that can host all this gear. Majority of data centers that were built in yesteryear, they were designed for 12 kilowatts a rack, 15 kilowatts a rack. They're in open environments that are air-cooled with kind of industrial HVAC systems. Now, today, we're 120 kilowatts. And easily That will double in the coming years. The question is, okay, if all these data centers don't have the capability to handle this, how are they getting deployed? Well, a lot of it is in new greenfield data centers. Easy to say, but not difficult to deploy. A lot of utility companies are saying, hey, it's 2 to 3 years before you can get hundreds of megawatts for large-scale data center deployments. Certain governments have put restrictions and moratoriums on where new data centers can be built. And that's globally. It's in Singapore, it's in Japan, it's in Taiwan, in Europe, moratoriums in the Netherlands, in Ireland, and even in the United States. You know, you hear a lot about Northern Virginia, and a lot of data centers in the Midwest are now expanding to other areas. And what are those other areas? Well, the interesting thing about large language model training, it's kind of batch-oriented. It's not customer-facing. So therefore, it can be away from the urban centers. So, you know, here in the US, you're seeing areas expand for new data center builds in North Dakota, Indiana. So other places that are a little more rural where power, land can be found, fiber can be brought in, where utility costs are reasonable. So it's interesting how we're seeing this arms race for new data centers to put capacity out to do these large language model training. Many of you probably know PUE. So PUE, power utilization. Traditional, you know, just kind of a general logical diagram of air-cooled data centers, server racks. Anyone that's been in any of these older data centers that have been built, no, it's pretty cool. It's pretty cold. Sometimes you got to wear a jacket. So I just have an example here of 22 Celsius in the environment. There's server fans in the servers that are blowing that cold air out to the rear, which is kicking out warmer air. That warmer air gets processed in a computer room air conditioner. Think of it as an industrial version of maybe even what the air conditioner in your home might be. Chillers with cool water, cool the air going through the crack. And then here's the example of pumps coming out. And I'm showing you an example of a cooling tower. Many factories and data centers you see also have heat exchangers, many of them on the rooftop as well. So, as I said earlier, you know, a lot of new data centers are being built. They look different than before. And this is an example of one that, you know, provides an optimal type of air cooling environment. There's open air, there's, you know, cold aisle, there's hot aisle. But this, or a variant of this, has emerged as kind of one of the most efficient ways that you can do an air-cooled data center, which really is a hot air, think of it as a hot air chimney or a plenum. Racks are rolled in from both sides. They pull cool air. They blow warm air up into a center conduit. Warm air rises. And then that warm air is then sent through a crack to cool it down, to then recirculate that through. This is an example where I'm showing it's the cooling ducts, which could be miles of cooling ducts in a data center. They're under the ground. Some hyperscaler data centers, you'll see the crack is actually up above the server cabinets. So it takes the hot air in directly and the cold air just falls from the ceiling back into the racks. So a few different variants that can affect what that PUE comes down to. But, you know, these types of architectures and PUEs you can see get, you know, 1.2 and below. If you're doing 100% capture of that air as close as possible to where the air is hot, you really can get benefits of efficiency. And just looking at the crack in this example, warm air coming in, chilled water going into coils, cooling that air, and then that being pushed into the floor tiles up into the ambient side of those IT cabinets. So what is the opportunity? Someone mentioned liquid cooling, you know, liquid cooling earlier. A lot of benefits to liquid cooling. It is a cooling technology. It has superior cooling capabilities, also has tremendous benefits in power. And we're going to talk about both of those things. Talked to over 90% reduction in server power cooling. You know, for those that know server designs, and a typical GPU server today that has 2 Xeon CPUs and say 8 GPUs, and those CPUs and GPUs, you know, anywhere between 500, 1200 watts on 1200 watts on each of those. those drive the majority of the airflow in a system. They have tall heat sinks, tremendous amount of power, up to, of the server itself, up to 20% of the power consumed can be just from the fans. And that's driven because of these hot chips. So if we can get more efficient at removing the heat from these hot chips with liquid cooling, now the fans, that whole design can be driven. They can run much slower. Power can almost be reduced of just fan power by 80%. And so, I'll talk a little bit about at the server level, you can reduce, just by going to liquid cooling, you can reduce the power of an individual node by 15 to 16%. And think about that, the amount that benefits you. We'll go into it more. And 40% reduction in power at the data center level. I talk about this in a later slide. So I already talked about the 15 to 16% reduction you'll get from power in the data center. When you design your data center for liquid cooling, and when I call liquid cooling, when I'm saying liquid cooling, it really is liquid cooling to the chip. There's liquid in every data center, but I'm really focusing on bringing liquid to the chip. Well, now you get rid of those, reduce those fans significantly in the servers in terms of their power draw. The cracks disappear, the chillers disappear, and really you just have two liquid loops. You have the one that's locally in your rack, and you have another one that's facility water that's taking the heated water that transitioned from the rack out externally and you're cooling it. And we'll talk a little bit more in detail about what that looks like. But the chiller, the crack, and those fans, the biggest power, biggest things that are consuming the power in that data center. So just a little high level of direct liquid cooling. How does it work? Upper left, direct liquid cooling cold plates. Many of you have probably seen these things. Very planar plates, but very specifically engineered. Inside of them, I'll use copper as an example, little copper microfins. Fluid is pumped through these things. It warms up as it goes over the fins, comes out and gets processed. That typically goes into a rack or row level heat exchanger. Typically with a gasketed plate heat exchanger doing a liquid to liquid transmission, and then that facility water going out to a cooling tower. So a little bit more simple, a little bit more straightforward. Water, if you look at just the laws of physics in terms of water versus air from thermal conductivity, I think water is 23 times better in terms of transmitting. So much more efficient way to remove heat from a system. In the rack, a lot of the liquid, as I talked about those little fins, they're, in some cases, the width of a human hair, those that have hair. Typically mixed with glycol. That helps for pumping, that helps keep some of the bio growth from happening. And also, speaking for Supermicro, we ship fully integrated racks with liquid cooling systems. And so we got to keep that stuff to prevent it from freezing as well in terms of going through the shipping process. And then there's a lot of research also going on the liquid itself and how can we make things more efficient. So the liquid has a lot of chemistry happening. The cold plates have a lot of engineering design that's going into them. Everything is about how do we make this even better than where we've started from. Liquid cooling's been around a long time. HPC supercomputers have used it for a long time, but it's been very boutique. It's been very white glove. We're going to do a little cluster over here. We're going to build it in 6 months. Where we are now, and one of the things Supermicro is doing, is we're bringing it in volume to the masses, hardened. So we talked a little bit about what happens at the rack. Cooling tower. So many of you may see, as an example of one of the ones we have at Supermicro, but many of you may see these cooling towers outside of factories or outside of data centers, kicking up all this white stuff. That white stuff is steam, not pollution. It's steam. Because this warm water from inside the facility that's been warmed up by the racks is getting pumped outside. And depending on what the temperature is of the ambient, if it's very cold outside, it'll cool naturally. If it's not cold outside, we actually spray water on it. And what happens to water when you spray it on very hot metal? It evaporates. So you see a lot of things, and that's probably one of the biggest areas, a lot of discussion in the industry about water utilization in data centers. That's probably the biggest area, is how much are you condensing into the air? Because they're closed loop liquid systems. So it's really about what happens in the cooling tower outside in terms of the amount of water you end up utilizing. And then cold plate designs, a lot of science, a lot of engineering going into these. How well do you know the chip? How well do you know where the hot spots are in the chip? How well can you simulate that? Like I said, we're talking about additive manufacturing capabilities to create, non-planar type of structures inside of these cold plates. So a lot of engineering going in there, and it can make, up to 35, 40% difference in how effective these things are and how efficient they are. So this will continue to mature as well. And then I talked about the CDU, which is really that thing that transitions the heat from what you have locally in the rack to facility water that goes out. Just a couple of things here, key design tenets. If you look at the lower left, capacity, this is one of the ones that Supermicro has that's in rack. And so it can support and cool 100 kilowatts with 32C facility water. But if you have much warmer water, it's still going to work fine. It just doesn't have as much capacity inside. So one of the things that's interesting about direct liquid cooling, if you're looking at a traditional air-cooled data center versus a liquid-cooled one, and you send water out to a cooling tower, and that water comes back in many cases with direct liquid cooling, that water doesn't have to come back in at such a cold temperature. If it doesn't have to come back in at such a cold temperature, that means you don't have to be spraying water on it often. That means you don't have to be wasting as much water. So direct liquid cooling can have benefits from that standpoint as well. And obviously features, availability is really important. So when things go down, if they go down, having redundant pumps, having redundant power supplies that can be quickly fixed with enough telemetry to be able to notice when something might be happening so you can take care of things proactively. And talk about telemetry, for instance. Liquid cooling, as you've seen, it's a closed loop system. It's a closed loop system from the chip all the way out to however you're deciding to cool it outside. I mean, if you have access to unlimited water outside and you can pull from cold water from the ocean, treat it, and pump warm water back out, maybe you don't need a cooling tower, but bottom line, it really is an end-to-end closed-loop system design, and everything has to work, and everything has to be optimized together, and everything has to be monitored together. So what are some of the bonus effects of direct liquid cooling? I talked a little bit, I've got a picture of a 10 kilowatt GPU server up on the right that has, air-cooled heat sinks that are about that big. You go to direct liquid cooling, and that cooling plate's about that thick. So you can get a lot of compression, which means you can put a lot more in a rack, which means you can save floor space at the data center level. Also, for anyone that has lived around air-cooled systems for a long time, if you have rows of heating elements and another row of elements behind that, well, that rear row gets preheated by the front rows. So direct liquid cooling is something where you can take liquid directly to each chip if you so choose. And there have been a lot of studies that showed with direct liquid cooling, you actually can get much better performance out of these GPU servers because they're not throttling or maybe even running above typical. And when I talk about performance and training, it's all about how fast can the training get done. And that's time to money. The sooner the training can get done, the sooner serving and inference can happen from it, and that's where the end user gets their revenue from. Talked a lot about the power reduction at the data center, the power reduction at the server level. Every amount of power that's reduced in the world is directly correlated to carbon emissions. And a lot of talk in the industry right now about data centers, the growth of data centers, and are they green or not, and what's being metriced. And then my second last bullet, there's no better source of heat generating than a data center. It generates warm liquid. Well, what else can we do with warm liquid other than just, create evaporation into the sky? Well, there's actually campuses being planned now where data centers are being built next to agricultural warehouses where they're growing lettuce. And what's happening is the warm water from the data center is going over to that agro facility and warming it in colder climates when it needs to be warmer. So there's other things that can be done. And we talked a little bit about PUE earlier, and there's even talk, well, if we can reuse that warm water, can we even get to PUEs that are less than 1? Something different to talk about in the future. And then lastly, for where silicon's going, liquid cooling is really the only way to support the roadmaps of the chips that are coming at the densities that they're coming at. So it really is an imperative, So a little bit talking about liquid cooling, but talking about what its benefits are. Building a data center is directly correlated to what is the power of your IT equipment. Well, I talked about you can get 15% reduction in power from your IT equipment. So right there, you can keep more money in your pocket from a data center build out for a given cluster size. And that can pay for your liquid cooling equipment. Secondly, OpEx. What is the operating costs over time? Well, in that data center, we talked about getting rid of the cracks, getting rid of the air handlers, getting rid of those industrial fans. The actually electricity and water bill that you're paying on a monthly basis between air cooling and liquid cooling, you could reduce that by 80%. So that 15% reduction in power from the IT equipment up to 80% reduction in your data center together, equals your bill is going to be 40% less. And whether you're doing a retrofit in the data center or you're building a new one, that 40% comes to play. And the example I have there is for a 1,000 GPU cluster at 18 kilowatts per hour. Over 5 years, that's $60 million. It's not chump change. That's that much more money that could be spent to buy more gear to allow you to train bigger models or actually get done more quickly. So talking about direct liquid cooling, as I said, it's been around a long time. One of the things Supermicro is doing is, and they actually started about 3.5 years ago, is how do we bring this to the masses in volume and harden it so things can be deployed quickly. Some of you in the press may have read about XAI and what they're doing in Memphis, Tennessee with their supercluster. 150 megawatt data center, thousands of racks of GPU servers, and happy to say that Supermicro is playing a big part of being the IT in that environment. Went from equipment arriving to turning on training in 19 days. Unheard of for something of this scale. Direct liquid cooled for sure at this scale. We talked a little bit about lead times. So where we are today, one of the things Supermicro does is when I talk kind of cold plate to cooling tower, we do all that. Cooling towers all the way to cold plate. We design it, we manufacture them, we have our own supply chain. Supermicro is a very vertical company. We design our own power supplies and manufacture them. We design and manufacture our own motherboards. We design and manufacture our own chassis and cold plates all the way out to that cooling tower. And so we control the supply chain, we control the quality, and with lead times, can be very quick to roll those things out. And then reliable. So I'll just tell you, we've been shipping thousands of racks per month for many months now. Rock solid. Rock solid. So once again, about bringing it to the masses in volume in a hardened solution that's easy to deploy and quickly to deploy. So a couple other things, rear door heat exchangers. Think of this as a crack unit on the back of the rack. Simple as that. You still have air-cooled equipment in the rack. It's still using cold air, blowing it over, exiting hot air. But what you have is you have a little, essentially a little cooling coil right at the back of your rack. And nice thing about this is it's capturing all the heat. You aren't getting the 15% benefit from doing direct liquid cooling, but this is typically used in areas where you don't have the AC handling capacity in the environment. It does increase your supply chain, increases your complexity a little bit, but it kind of acts as a distributed air conditioning unit in the end. It basically pulls that hot air through those cooling coils, just like a little local crack would be, and then exits air that comes out in the ambient space. And then what we see is, customers that want to do a data center, but they've purchased a manufacturing facility for instance, that doesn't have the cooling capability yet. So they'll bring this in and put this on all of their racks as an intermediate step until they can get things deployed the way they want them. And then also a lot of talk, a lot of research, and a lot of benefits around immersion liquid cooling. Number one, captures all the heat 100%. So it's really wonderful from that standpoint. It really made it big in Bitcoining and crypto mining. If anyone has seen immersion tanks for crypto, boards just peppered with crypto mining chips, just submerged. Difference between that type of architecture and what we're doing in IT, we've got 1200 watt chips. And so we want to cool directly to them, which can be done here also. But we've got a lot of cables. We got a lot of cables, power cables, networking cables. And it's all been, the IT industry's all been designed to be deployed in air today. So one of the things about some of these dielectric fluids is that they get contaminated from the insulators on cables. They get contaminated from flux on the boards. Transformers that were designed to be run in air now change their properties with dielectric materials. So I think it's a great technology. It's coming and it is emerging, but I will say this, the world is going through a revolution with direct-to-chip cold plate technology today. I think this will find its place in the bigger IT data center in coming years. For instance, I think about I/O. I/O is something, and connectivity is something that's really quicker. Everyone wants to do faster I/O over copper and over copper cables, and how far can we extend that? Well, that's going to run out of steam at some point, and we're going to be bringing optical cables directly out of the chip. Well, when we're doing that, can you still get a cold plate in there? Or do you have to box up this chip with all of its optical cables in some kind of an immersion box? Not necessarily a big tank, but cool it with dielectric in a different way. So I think we may see it in a different form than maybe the way it's being deployed in crypto today, but I think it will have a need in the future. For those that don't know, Supermicro, company founded here in San Jose 23 years ago. So been around a long time. And they're a very unique electronics IT manufacturer because they're a company that never outsourced manufacturing. Our campus down by the airport is design and manufacturing right next to each other. Now we've expanded that in Taiwan. We added design and manufacturing there, so we've expanded it. But part of the belief is when you're doing systems like this, design and manufacturing, especially for NPI, new programs before things are stable. Having those teams co-located, no better way to be quick to market. And I'm a firm believer in that as well, from data points that I've had in the past. Hardened technology, as I talked about, and like I said, production across many different areas. And in this boom we're in with LLMs, the company doubled in its revenue and with projections to double again. And lower right, and talk about capacity. So our manufacturing capacity today, 5,000 racks, and over 2,000 of them direct liquid cooled. And if we had more manufacturing capacity, we'd be moving that much more today. Just AI crystal ball a little bit in terms of just some things to think about. Not that there's any necessary answers, but what's changing in the future? If we think of the last 10 years to where we are today, domain-specific models, country-specific models. We talk a lot about large language, but graphics, video, a lot of things that are going to change there. LLMs, a lot of talk about small language models. Hey, this big model that's generic is great, but I've got my unique data here. How do I rag that in so that I can create a smaller model that works just for my stuff? I think there's a huge movement coming in AI inference. Right now, all the rave is training, but training by itself doesn't generate revenue. It's all about what you can use that model for. So I think there's a huge wave of inference coming, inference at the edge, very vertically aligned in terms of retail or manufacturing or the medical side of things. And then, further compute architecture. What gets optimized at the data center versus the edge, training versus inference. And, transformers versus flexible accelerators. Transformers are the things that really brought what Google does with search and what ChatGPT does. But if you look at most GPUs today, they're, I don't want to say general purpose, they're specific purpose, but what they can do 32, 64-point math. They're good for HPC. They support a lot of different formats. They're flexible. They're little number crunching engines. Versus, there's architectures that are out there looking, saying, hey, I'm going to do a chip that can only do transformers. Not flexible for anything else. Could be a game changer. Could be. Memory tiering. We talk a lot about these things. If you remember, it was all about how much can you fit in a certain amount of memory. That determines how you partition your model. I spent a lot of time in the server space, and actually my first server that I was responsible for when I was at Dell was a 4-socket server. And what baffled me was most customers didn't buy that because they needed 4 CPUs of horsepower. Most of them bought it because of the memory footprint it could support and the bigger data set sizes that could be supported in one NUMA domain. And so when we talk about sizes of NUMA domains, that's why you see a lot of these GPU players talking about more HBM memory, talking about more cluster technology to create a coherent memory domain. I think that's going to be a frontier that continues to grow as well. Direct liquid cooling's here today. Talked a little bit about when and if immersion takes off. I think it will come. And then lastly, I love thinking about it. Artificial general intelligence. When will that be out there so we can talk to it and have meaningful technical conversations? That's it. I want to thank you for the time. Appreciate it. Is it good?
That was right on time. Thank you. So we have 10 minutes for questions. Do you have one on Slack you would like to answer?
We do have a Slack question, and thank you, Tom, for the presentation.
Sure.
So this one was upvoted by a few people, but it was originally posted by Christoph Novak from MLID. He was really interested in how hot water might present a maintenance challenge with any risks that are posed by having failure in those water loops inside of the data center.
By the way, before you answer, we have 2 mics along the walkways. So if you have any questions, just please line up near the mics inside the auditorium. Yeah, go ahead.
So hot water, great question. I mean, I think this is one of the spaces where obviously you have to know your end-to-end system. And you have to know what temperatures could be supported, what temperatures could come up to those things. So all your components have to support those temperatures. But I will say this is, one thing that isn't shown, a tremendous, design for maintainability, the monitoring, the telemetry, the automatic valves to shut things off. I mean, believe me, liquid cooling does have different maintenance workflows today than air-cooled data centers. And that's what the industry is maturing in today. And honestly, I'm not seeing challenges with it.
Please, go ahead.
I have a question regarding the temperature of chips. Have you done any research on what's the optimal temperature for those chips to operate at? Is it how cool is cool enough? How cool is too cool? Any of those range you have?
Well, for myself, how cool is too cool? Obviously, there can be things that are too cool. Not all chip vendors provide the same amount of margins. So how I would answer that question maybe 10 years ago might be different than today because margins, I think, are a bit slimmer. That said, I think keeping away from spec, absolutely very important. But looking at what the cooling spec is and keeping it significantly cooler than that, like I'll give an example on Xeon chips. If you can keep them cooler and keep their current levels down, they have things called turbo frequencies. And in many cases, you can actually run almost like a under warranty overclocked situation if you can keep those chips cool. So it really depends on the exact chip and the vendor that they're coming from. But definitely stay away from spec.
Run them lower because directionally, if you run them at low temperature, you would waste less energy through leakage, right? You would get more performance for the same watt.
Exactly right. But there's a range in terms of, too cold could, mean transistors get too hot and, things don't man. So there's a range. And so, but definitely keeping it below spec is good.
Do we have a question on Slack we should take?
We have a couple more questions on Slack. So someone asked about, I don't know if you saw the presentation last year at Hot Chips by Fabricate Labs, which did 3D printing of cooling solutions, if that plays at all into your strategies for doing local cooling.
It does when I talked specifically, I had the slide on cold plates and I talked about additive manufacturing. If you've seen some of these cold plates that actually have had additive manufacturing in terms of creating tubes that have holes in them in copper inside of these, there is a place. There is a place where that can play. That's the only one that comes top of mind right now, though.
The gentleman over there, please, go ahead.
Hi. I was wondering if there's any emerging standards for the galvanic compatibility between the heat sinks and other parts of the loop that's all touching the same liquid?
Great question. I got to admit, I'm not an expert in the space, but sure makes sense. It definitely would make sense to have some industry and standards there.
Shall we take a question on Slack?
Certainly. This is from Tom Gooding from IBM. He was interested in if the higher altitude data center locations might have more implications with liquid versus air cooling. Does that different atmospheric pressure impact the way that somebody might think about how they solve the problem?
Great question. Honestly, I hadn't thought about it. It definitely comes into play in air-cooled data centers, without a doubt. I honestly don't know. In the liquid-cooled systems, they are closed, pressurized loops, until they get out to the cooling tower. I don't have a good instinct on that right now, but it's a great question. It's a great question.
Okay, thank you.
Yeah.
Gentleman over there.
So for air cooling, so how do you think, is there a design limit for air cooling, for per rack, like 15K or 20K? You're considering some, existing data center cannot go to liquid,
Yeah, great question. And I'll maybe change the question from a per rack standpoint to maybe a per system standpoint, because I think it's really a function of what your topology of your server is. As I talked about in air-cooled systems, if you have a row of 4 GPUs that are generating heat and another row of 4 GPUs behind it, it's these one behind that are going to limit you in terms of what you can do. But I will say this, if I showed the picture of the heatsink, the air-cooled heatsink, you can't just make those infinitely tall and get linear performance. In fact, we're seeing, maybe a 3U heatsink is something that gives decent benefits, but there's really trailing off benefits you get making it taller than that beyond. And so then how much of that power comes into a rack, what you can do. I think I showed on one of my other slides, maybe 25, 40 kilowatts per rack is being done today in air-cooled situation. I just think about any time you have these dense, high-power systems, if you can liquid cool and save that 15% of your power, it's a win across the board.
One more question from Slack.
Okay.
Sure. This one's from Eric Swan. He's interested in if people have looked at directly sealing the cold plate to the silicon so that it's attached, directly to the silicon backside. He's wondering if that gives you a lot of efficiency advantage by reducing the cold plate to thermal interface.
100%. In fact, I didn't mention it in the presentation, but the science of what the thermal interface material is that's bringing that chip together with that cold plate absolutely plays a huge role. It plays a huge role in what the thermal transfer is, plays a huge role in manufacturability and long-term reliability as well. So a lot of science being done in there, just like there is with air-cooled. So I think you're seeing a lot of thermal interface materials that might be indium solder with preforms today. It's another area that there's a lot of, I think there will be a lot of ongoing advantages as well and improvements.
Yeah, no doubt there's a lot of innovation happening there.
There is.
There are a lot of startups that are actually building innovative new cold plates, as well as CDUs. Those
Absolutely.
seem to be the two areas there's a lot of work going on.
Yeah.
One last question.
Yes. Sarah Biabani, as someone who started her career working on liquid-cooled vector processors, I appreciated
There you
your
go.
talk. You had the slide on the CapEx and OpEx numbers, and you've not really broken down the cost of liquid-cooled components. There's copper involved, there's it's expensive, right? And then there's also the added weight and all this kind of stuff. So that has an impact. So what are the other factors in the cost of liquid-cooled components?
So if you think about, simple way to think about an air-cooled data center versus a liquid-cooled data center. In this side, you're plumbing a lot of air ducting that are heavy, time-consuming to build. In this side, you're plumbing a lot of liquid pipes. So in both cases, there's a lot of plumbing. In the air-cooled side, you've got cracks, you've got chillers, you've got pumps. On this side, you don't. On this side, you don't. So it definitely saves your cost. From the analysis that we've done, it shows it's very much a wash in terms of if you're designing the way air-cooled data centers used to be to something that's optimized for direct liquid cooling. Very, very similar. And separate from what it takes for CapEx, just the amount of power you can save on an ongoing basis just puts more money back in your pocket.
Sorry, is it to quantify it, since we do quantification here, is it 2% close to 2% the same, or is it,
Yeah.
How close is it?
Very low single-digit percentages. Think of that.
Well, we've run out of time, so thank you
Okay.
very much, Tom.
Thank you very much.
Wonderful
Appreciate the time.
All right. I think we're running on time if you ignore the 15 minutes we lost because of the power outage. But I think we can recover the 15 minutes by reducing the coffee break. But what we'll do now is plow through to the next presentation. And right after that, you'll have the coffee break. And the coffee break, instead of 30 minutes, if you don't mind, if you could cut it down to 15, then we can come back and wrap up on time. How does that sound? Thank you. So the next presentation should be very interesting as well. And some of you who haven't had an opportunity to ask questions after the first talk will absolutely be able to ask these questions after the second one, because this is also about data center cooling. It's from Dr. Ali Heydari from Nvidia. So we've heard from Supermicro about how they're handling the problem. So now we're going to hear from the company that's actually the source of the problem. So Dr. Ali Heydari is a distinguished engineer and director of data center cooling at Nvidia. At Nvidia, he's in charge of all data center technology development. In this role, he's developing direct-to-chip liquid cooling technologies and using cold plates, cooling distribution units, and manifolds for cooling NVIDIA's high heat density. Prior to NVIDIA, Dr. Ali worked at Twitter and Facebook, where he designed their data centers. And also, Ali started his academic career as an assistant professor of mechanical engineering at Sharif University of Technology in Iran. Dr. Ali got his PhD in mechanical engineering from the University of California, Berkeley, and he has over 25 issued patents in data center cooling technologies. So we've got a real expert in this space who's going to come and tell us what's the latest in this space next. Ali, you're up.
Thank you. Clicker, forward, and back.
Okay, thank you.
Others, pointer.
Thank you. Thank you for the opportunity. I'm very proud to be standing here in front of such a crowd of experts. I'm a product of Bay Area. I've been in Bay Area for the last 30 years of my life, and I've been at Stanford, I've been at Berkeley, and I'm really proud of presenting what the industry is going through today. I'm not a software engineer, but I have to give a little bit of a talk about software engineering to describe why this transition is happening. I'm a mechanical engineer. I did my PhD in
liquid cooling of nuclear reactors, and very interestingly, the same application of nuclear reactor cooling, I'm finding it very closely in data center cooling and GPU cooling. So I'm going to walk you through a journey, but first I want to talk a little bit about the background of where this journey started and why did we not converge where we are converging into liquid cooling in past with Craze and IBMs and what we had before, and why are we converging in mass scale at this time? So the starting point is deep learning. And so the software evolution of deep learning is changing industry, it's changing science, it's changing engineering. The vehicle behind that is generative AI. And we all heard about generative AI. And I think about generative AI as the industrial revolution of our time. Industrial revolution started when generators created electrons, and we enjoyed having electrons to produce electricity. AI, through generative AI, is going to produce tokens. Tokens that we produce in our AI factories is equivalent of what we have in, or what we have seen since the era of the Industrial Revolution in the years to come. So this token is produced in our factories, and the way that the three elements of AI, data centers, and accelerated compute come together has allowed us to create this massive compute and generative AI in ways that we can solve problems that we could never solve in past. I used to teach computational fluid dynamics. I used to teach CFD. Anybody who does CFD today can say that it takes you sometimes 45 minutes, sometimes half a day, sometimes a day. Large-scale models of computational protein, large-scale models of weather forecasting. We all know that. These are all massive problems. Some of them show up in accelerated compute, which we used to call HPC. Some of them are showing up in the form of generative AI, which we call ChatGPT, a moment of what we've seen, what this generative AI can do. So when these three came together, it revolutionized and was able to produce capabilities that we would never be able to do in past, and that's where we are. Basically, we are seeing two avenues opened up in front of us. Accelerated compute and generative AI solving problems that we could never solve in past. The way we approach this, we all know about factories. We have all built factories, and we know the product of the factories are what is shipped out. Our factories, which we call data centers, is producing tokens, and generative AIs use those tokens. These tokens, think about like large language models. You have a large language models. It's a product multiple tokens that comes out of each one of those modeling of the parts that make a sentence, make a paragraph, make a page, and that becomes, each one of them become tokens. Creating those tokens require computational capabilities. Those computational capabilities require massive amount of CPU and GPU, and that's where we are kind of starting our journey. So if I look at that chart that you see up there, you see that the flops, petaflops of computation, if I compare a petaflops of computation that today are supercomputers, Frontier, others that are in the ranking today, can produce them at a higher, slightly higher than my brain, human brain, but at the cost of power. My brain takes about 15 watts to produce a petaflops of 1,000 petaflops per second. If I had to do that in a data center or an AI factory, that takes about 22 megawatts of power. That's a massive scale change. 22 megawatts of power compared to 15 watts of power. Both of them generate logic. Both of them generate what we can go to ChatGPT and ask for a question on Copilot or Gemini and others. We can see them do the same thing. But now we have to deal with the scale of power. Scale of power comes at a cost of heat. Now we have to remove this heat. This power has to be generated to produce this amount of computation, whether it's AI through HPC, accelerated compute, or it's through generative AI. This amount of power generation requires massive amount of innovation in removing heat. 5 years ago, I started at Nvidia, and I started looking into this problem very seriously, and we started building the basic blocks of what today's industry requires. We looked into how we can go into large data centers, produce what used to be 5, 10, 15, 20 kilowatts of racks that can produce basically computations, and make them into hundreds of kilowatts of racks. And how can we build that scale of compute in a data center, and how can we achieve the sort of service level agreements that we have in an everyday data center? So I'm going to go to next step, which is all the steps that we went through. So we have data centers that produce heat, and this heat in the tradition, as Tom mentioned before me, are removed by air. So air removal through data center, through whether it's a raised floor or whether it's a slab floor, cryo units, computer room air conditioning. Some I use abbreviations, I mentioned that, so make sure that I make myself clear. It's traditional, it's known, and is a known art in the field. We are bringing in liquid very close to the source of heat, which is the GPUs in this case. The GPUs can go up to kilowatt, above that, and several, it can be 1,200, 1,500 watts. As a traditional CPU can be like about 100 watts, 150 watts. Now, as Tom mentioned, as you increase the power of the GPU or CPU, if you continue on the path of air cooling, what happens is you're not going to be limited by the physics of air removal. I can remove heat any day of the week, up to 100 kilowatts per rack, even more with air cooling. The problem is the limitation is the size. My racks are limited to a certain size. Data centers are basically building blocks that have been around for 70 years with air cooling. They have this formal fashion building of these racks and rows and cold aisles and hot aisles where this equipment comes together with networking and power distribution, what have you. Now we have to bring in this huge pods of data center in form of GPU racks and remove heat through them. And the limitation with air cooling was that the size of the heat sinks would become too large. I can remove 1,200 watts of heat from a GPU module, but that requires 7U height of, or 6U height of a heat sink. What if I change that 7U height of a heatsink to 1U? And when I say U, it's about 1.75 inches, very small pizza box. What about if I remove that and put cold plates, and I can now create massive amount of computations within a rack, traditional rack, X number of U's, 44 U's, 52 U's, height rack. And then I can basically now bring this family of GPUs and CPUs, networking equipment, all of them in one rack, produce the sort of computation that I need to produce, put number of racks next to each other, produce a pod of these racks, call it a superpod. That's what we call it, a superpod, supercomputer. Now this supercomputer now occupies a very clear space domain. One of them is shown in this picture, that I'm able to go surgically remove heat using liquid, warm liquid, and keep the computations and GPUs happy. And therefore, that's the steps that I'm going to walk you through how we did that in the last 5 years. So if I look at the traditional data center, what you see on the right side remains always the same. Whether you have chilled water facility or you have economization with dry coolers or cooling towers, we are not going to touch that. We're going to stay with the existing data centers. And what we had in past was we have cryo units, computer room handling units, where the racks were sitting, and these cryo units would basically remove the heat that was absorbing through the process of removing, pushing cold air into between cold and hot aisles to the outside. So it's basically a heat exchanger. Takes heat from the racks, dump it outside. Outside can be expensive, like vapor compression, chillers, or it can be like dry coolers, economization dry coolers, or cooling towers. That's that's been the practice for the last 70 years. When things started to go up in power, we started seeing in-row coolers. In-row coolers would come in, sit in between racks, and basically you've seen the last 70 years, liquid has come closer and closer to the racks. So in-row coolers would take liquid from the chillers, you still have an element of air cooling, and the in-row coolers would produce colder air closer to racks. Very traditional way of heat removal for the last 15, 20 years. After that, we've seen rear door heat exchanger. Rear door heat exchangers does the same thing, and they have been doing this for decades, and the liquid is getting closer to the rack at the rear of the rack. The change happens when the rack itself now needs liquid. So there are two ways of doing it. Whether this happens in a traditional existing data center where you don't have any plumbing, you don't want to bring any liquid inside of the data center, where we have what we call the sidecars or heat exchangers would sit next to a rack, and these sidecars would take air from the cryo unit and push liquid inside of the racks. That's called the liquid-to-air heat exchanger. So there are two ways that moving forward we're going to remove heat from those racks where you have cold plates and have a hybrid of air and liquid cooling. One way is through the liquid-to-air heat exchanger, which has advantage of being able to do it today. So we thought about the industry is going to go through this transition. Not everybody is going to be able to run massive liquid lines, plumbing, and changes to the data center. They're going to be wanting to build what they have. I mean, XAI as an example. Others, that are showing up, existing data centers. So we work with industry to create these sidecars or liquid-to-air heat exchangers. And these sidecars can now today remove maybe about 100 kilowatts, 120, 130 kilowatts of heat from a rack. Not that much, but it's a speed of light. We can use them instantly today. So we can bring racks with liquid cooling, use sidecars, and with no changes to the infrastructure, basically becomes 100% air cooling. Within the rack, you have a liquid cooling with a sidecar that produces liquid inside of that rack. And that's how we remove heat today in a data center. Remember that the right side remains the same. There's no change to that. The more important one is the liquid-to-liquid, which we call CDUs, cooling distribution units. And people talk about efficiency, ask about the space, what are the advantage and disadvantage of this liquid phenomena coming in data center. I can summarize it this way. A single CDU, cooling distribution unit, can be up to maybe 4 megawatts, 2, 3, 4 megawatts. The space of that is like about 4 feet by 4 feet by about 6, 7 feet. That is massively smaller than a traditional cryo unit. Cryo unit could be 6, 8 feet wide, 3 feet deep. Massively less power consumption. It has 2 pumps, one for redundancy, one for pumping liquid, and I'll talk about the liquid a little later. And the efficiency of these units are extremely high. So now we are talking about business. Now we have something in our hands. I can have one box that can remove 2, 3, 4 megawatts of heat from my racks. All I need to do is plumbing. Do plumbing, bring liquid in, and make sure that liquid that goes into the racks are reliable, as good as what used to be with the air. So that's a transition for the last 70 years. What we're going to see in the years to come is we're going to see deployment of either liquid-to-air or liquid-to-liquid CDUs next to the liquid-cooled racks, and ability to remove heat surgically from these cold plates attached to the heat source GPUs. When we look into liquid-to-air heat exchanger, we take them to our labs. We don't know what the future is like. We don't know if the next rack is going to be 100 kilowatts, 200 kilowatts, 400 kilowatts. How far can we go? Is there a limit of how much we can increase this rack density? What I know is definitely we want to create these AI tokens and generative AI as fast as we can. So we have to have capability to do it. So in our labs, we create these emulators. These emulators can be any style of, any amount of heat generation. And we experiment with these cooling units, in this case, liquid-to-air heat exchangers, and work them out to see how far we can go. What's the limit of their operation? Somebody asked about the temperatures. We look into the temperatures. What is my warm water temperature? What's the return liquid temperature? What's the liters per minute? What's the CFM, cubic feet per minute? What are the limitations? There are serious limitations with liquid-to-air heat exchange sidecars. And we think that there are speed of light, but they're not going to carry through large scale. We don't think that this CDU heat exchangers are going to stay with us for large heat density racks. We go to liquid, same thing, same phenomena in our labs. We create this digital twin phenomena that we create in our labs, and I'm going to walk you through that. Large CDUs, liquid-to-liquid CDUs, multiple racks, emulating heat load with the heat load emulators with cold plates attached to them, and removing heat surgically from the source of the heat, which is, in this case, like emulator heat sinks attached to the cooling distribution unit, pushing liquid out. So that's how we build the systems. That's how we create them. So if you put them into practice, that's how they look up. So this is the digital twin omniverse vision of when a data center with liquid cold come together. This is a hybrid data center. On the right side, you see CRY units. On the left side, you see a combination of the racks. This is on NVL72 with 72 GPU, and which has 2 GPUs, 1 CPU, as you can see in this image, in the rack. And each one of those servers are liquid cooled. And the liquid cooling is happening with the sidecars attached to them, and the sidecars get colder from the CRY units, and the CRY units basically remove heat by basically the process of the from the liquid inside of racks. And that's how the racks maintain their temperature inside of GPUs, and we can maintain large clusters in a small space. I think I need to click on the second one. There is a second video in here that shows the liquid-to-liquid. So this shows practical how this design of this liquid-to-air and liquid-to-air. So this is the one that I want to focus on more. You can see on the left side, you see the CDUs and the row of the racks, row of the CRY units. You're pushing about 85% of heat to the liquid. We're taking 15% of the heat from the air. The liquid plumbing shows that the plumbing of the liquid removes the heat with the CDUs from each one of these racks, with the GPUs that are cooled by cold plates attached to them, with manifolds distributing liquid inside, and the CRY units that remove heat, what we call residual heat. So if I have a 130 kilowatts rack, I have about 120 kilowatts that I can remove with one CDU, and many rows of these, racks of this in rows, with residual heat being removed by the CRY units. So the CFD and the flow network modeling, I'm going to walk you through that, because these are tools that we needed to generate working with the industry to be able to create this style of cooling. And so that shows very uniformity of heat removal with ability, what I'm showing in here, in very small space, up to 6 megawatts of heat generation within the racks. So we've been working with the industry to create flow network modeling. CFD, everybody's familiar with that. So we have computational fluid dynamics, CFD tools, ANSYS, Cadence. Those are all in existence and practice. What was needed is to add liquid to those modules. So we worked with industry, in particular in Cadence, and added liquid cooling, flow network modeling to their models. So now you have a hybrid data center. This hybrid data center has a combination of air cooling and liquid cooling, and I need one tool. And this tool is not capable of removing with a combination of air and liquid cooling combined into one software tool. I'm going to run a video here that shows the Omniverse, how this works into Omniverse.
Nvidia builds the world's most advanced AI supercomputers. We start by creating their digital twins in Omniverse. Our latest supercomputer is a large cluster based on a liquid-cooled system with 2 racks, each containing 18 Grace CPUs and 36 Nvidia GPUs. connected by NVLink switches. We're retrofitting an existing data center, so Kinetic Vision helps generate a 3D mesh from Navis LiDAR scanners and uses Preview 3D's point cloud processing tool to clear the existing racks, leaving an empty data hall. In Cadence Reality Digital Twin Platform, powered by Nvidia Omniverse APIs, our engineers unify the multi-CAD facility and rack datasets and visualize in full physical accuracy. To optimize network topology and train our operators, we use NVIDIA Air Network Simulation Platform connected to Patch Manager's cabling layout tool with Omniverse APIs, letting us bring this data into the Omniverse digital twin in Cadence's platform. With Cadence's solvers accelerated by NVIDIA Modulus APIs for physics ML workloads and Grace Hopper, we can then simulate performance of the Air and new liquid cooling systems from partners like Vertiv and Schneider Electric. This helps our engineers plan for what-if scenarios. NVIDIA and our ecosystem of partners are bringing up new AI factories faster than ever with NVIDIA Omniverse and AI.
Everybody talks about digital twins. We are building the next generation digital twin for computational fluid dynamics. Think about large language models. We have tokens in large language models. We are working in bringing CFD, flow network modeling, everything that you've seen in this conversation so far, which is probably very boring. It's all last plumbing and what has been done in the last 70 years into the generation of AI. We are bringing in ways that we can simulate and build data centers real time. So basically, we are eating our own food. We are trying to teach our GPUs and the servers that NVIDIA builds how we can accelerate designing and building our data centers using CFD tools and flow network modeling that's embedded within our Omniverse, which is basically a digital twin tool of a display. It's a display tool. Behind that is basically the process that we're building. So the short version of what we are doing is we're not solving neighbor success questions. We have a training. We can have a training, just like a training and inferencing of CFD versus application. So we can train our CFD tools in an Omniverse digital twin environment with tools that we have. Modulus is one of our tools, and existing tools that we are generating. And think about build this data center very realistic to the spec of everything that we need to know, with the ability to run real-life CFD. So that requires immense engineering and capabilities. So we have the software tool set, and what we are doing today with industry is putting together tools that we can simulate these individual elements of this digital twin. So CRY units, CDUs, cooling distribution units, they all need to be digitized. There is a need for creating digital twin. In a future data center, what I can think about is like you have designed a layout 3D from a SketchUp all the way to CAD and Fusion 360 to Omniverse, and you have a digital twin data center. You decide to move a rack from a location to a location. You decide to change the rack density. You decide to bring different style of putting these racks of servers together. You want to change this from North Carolina to Singapore. You want to change the method of heat removal in the ambient. This has to be done instantaneously. That's what we are trying to do with this digital twin. So one of the research projects that I'm working with my team is creating digital twins of data centers, working with industry, basically asking them to create digital twins of their cooling distribution units, CRY units, and so that becomes the library items within our software tool set. One topic that's of interest for liquid cooling, these are research topics that I'm working on, is fluids. I think somebody asked about what's the reliability of the fluids. So for the last several years, we know that liquid, in this case water, and the particular form of water that we are using is a percentage of propylene glycol, 25% propylene glycol with treated water, PG25. We are bringing that PG25 basically as a way of removing heat. Think about we are replacing air with PG25, 25% propylene glycol and a water mixture. Now, how good is that? what's the potential of the biogrowth? What's the efficiency of that? So we build labs. We do a lot of this research works based on standards, ASTM standards, building emulators, see the reliability, what we call a vetted material compatibility. We're changing the world. We've got to make sure that if we are changing, if you're prescribing the world, that you can remove air for 85% of your heat removal and put this liquid, PG25, instead of that, that has to be good enough. It has to be as reliable as air. And that, for the last several years, we've been working within our research labs, looking into the compatibility. So we have a list of vetted material compatibility, goes part of our standard reference design. We distribute this to our partners and data centers and CDUs and whoever is part of this partner network, and they know what works within our ecosystem. So we do a lot of tests and making sure that we have, as far as the vetted material. The other issue is like as you increase the power, as your drag densities increase, there's a demand for higher amount of liquid. It's a very simple math. You want to remove more heat, you either reduce the temperature or put more liquid into it, more liters per minute or LPM of liquid inside of it. Now we can go to certain temperature. We're not going to go probably cryogenics today or build quantum computers 4 degrees Kelvin. But with the tools that we have to ensure that our data centers are leak-proof. There's no potentials for leakage. If there's leakage, we have ways of containment, and that we have ways of managing the fluid velocity. One of the challenges of liquid is the fluid velocity. As opposed to air that doesn't eat anything, liquid eats. And if you have copper in contact with liquid, if it's impinging, it can eat away some of your copper, especially at higher flow rates. So we are researching on how fast can I put this liquid inside of this scarped fin cold plates, which has 100 microns fin structure to remove heat, and what type of material works best. Lots of research work in there. The other area of research that we're looking into is the next generation. Now we have changed the world from air cooling to liquid cooling. What happens next? Is single-phase liquid is the end of the story? If we go from 130 kilowatt rack that we're releasing with NVL72 to 2, 3, 4, 500, is there a limit? Can I go to a megawatt rack? If I go to that megawatt rack, what type of cooling do I have? As Tom mentioned, as the power of the GPU goes higher, case temperature goes lower. In other words, that's a phenomena that we've been observing throughout the industry, and we want to make sure that we have capabilities of maintaining that. So there is research that we are looking into many ways, whether it is immersion cooling, whether it's a phase change, any which way that we can look into the future of data center. Me and my team are looking into ways that we can facilitate this transition for higher density racks. Somebody asked about the efficiency. So we've done extensive work on power utilization efficiency and TCO, total cost of ownership. We published a paper. There's a reference in this paper that was published last year in Interpack. Summary is very simple. You remove air, you're removing scavenging ways of removing heat with surgical ways of removing heat with liquid. When you do that, you have capability with warm liquid not to use chillers. You can use dry coolers. You can use cooling towers. You can bypass the chillers because you don't need that cold temperature. You can go up to 45 degrees C as our working fluid PG25. So that gives us immense amount of ability anywhere in the world. Anywhere we do lots of data center analysis, whether it's the most hot tropical location in the world to the coldest places in the world, we can deploy our racks with what we call approach temperature between the two liquids, whether it's ambient, is maximum 34 degrees centigrade, 40 degrees centigrade. How far they can go, we can make sure that we have a transition to what we need to have. And that transition becomes cost saving. If I eliminate chillers and our chips are warm water cooling, I'm able to remove heat with liquid as opposed to air. Can get up to, as I said in here in this paper, a 12% reduction in the total server power because we are eliminating fans, 28% reduction in facility power, 15% total data center. So I'm eliminating fans, I'm reducing dependency on chillers, and I'm surgically removing heat with much higher power utilization efficiency than air cooling. So that way, when you talk about liquid cooling, absolutely lower costs, both in terms of the installation costs, operation costs, and efficiency. We're looking at sustainability. That's one big issue for us. We are building data centers that are 2,000 megawatts, large data centers. These massive data centers that are popping up different parts of the world are, massive problems. Carbon footprint. We don't want to be a company who's responsible. We're thinking ahead, making sure that as we generate these AI factories, we're also very responsible citizens of the world. So we're working with a number of research institutions, how we can harness that heat. Now, it's not going to be very simple. It's not going to be, straightforward. But as an example, as we can work through the problem, I can bring in warm liquid that's living on racks. If it goes to 85, 80 degrees C, something above 60, 70 degrees C, I can run absorption chillers. And I can use fuel cells. I can use the heat rejection that we have away from traditional heat reuse, which is district cooling and what it has been known. I can have a data center anywhere in the world that does not require basically district heating like Nordic regions, but I can develop data centers that can produce electricity based on its waste heat, that can run that waste heat as a supplement to an absorption chiller to produce cooling. Those are the research areas that I've talked throughout, many consortiums and universities like Stanford and others. We need researchers to focus on this. We need both research institutions as well as industry take this issue very seriously, and we are working very aggressively in this matter, because once these data centers are built, when the demand through AI goes through the roof, we need to make sure that we have ways of managing that heat release. We don't want to warm the air. Climate is already too warm. We don't want to do that. Just like hybrid car, just like anything that we've seen, we want to utilize that waste heat and produce something meaningful and useful out of it. So one of the areas that we are aggressively working on with institutions such as universities and research centers and industries is how we can sustain data center. How can we have a meaningful heat reuse and ways that we can capture this amount of heat to something meaningful? I think I'm going to end my talk with a very innovative work that we are doing. 1 minute. We were granted a project through Department of Energy, ARPA-E, and I want to show something in here, thinking out of the box. ARPA-E cooler chips put out a funding opportunity, FOA, last year. Nvidia, we put a grant request into it, and we won that request. And we produced a project called OmniCool. Let me go back. So, since I'm short, I'm just going to run the video, let this talk by itself, and I'm going to explain to that a little bit later.
As part of the ARPA-E Cooler Chips program, a team of industry and academia experts, including Nvidia, Vertiv, Boyd, the Durbin Group, Binghamton University, and Villanova University, have accepted the challenge to develop innovative cooling technology that can lower the environmental impact and costs of data centers. This cooling technology can achieve the lowest possible limit for DC energy consumption. When deployed, the cooling system will enable IT equipment to operate inside a shipping container, ideal for harsh and remote environments. NVIDIA's advanced 3D simulation environment, Omniverse, will be leveraged to develop a digital twin of the entire system and its advanced cooling technology. A single rack scalable unit will be built to emulate the system's performance. The immersive tray emulators will be utilized to test and develop hybrid systems, where direct-to-chip pumped two-phase technology will be used to cool the high-power components, while single-phase immersion will be used to cool low-power components. This approach will allow the use of extremely high-performing two-phase direct-to-chip for the highest thermal loads in an all-liquid, rack-based cooling system. The concept includes all levels of this deployment, addressing all of the program objectives. an innovative cold plate technology will be employed, operating with a green refrigerant. Two-phase flow visualization techniques will be utilized in designing and optimizing the cold plate architecture and defining the best operating conditions for the system. Additionally, CFD simulation will be utilized to optimize the flow and temperature distribution inside the immersion tray. On the rack level, the conventional coolant distribution unit, or CDU, will be replaced by an in-rack distributed pumping and flow separation system. The flow separation system will separate the vapor phase from the liquid and only direct the spent vapor back to the condensing unit, further improving system efficiency. Similarly, the immersion manifolds will be connected directly to the heat rejection unit. Multiple identical racks will be connected with each other to emulate an IT cluster. All the racks will be connected to external heat rejection units with coil array coolers, which can potentially reduce the cooling tower footprint by 4 times. As a result of the integration of these innovative concepts, the total cooling system power consumption is expected to be reduced to less than 5% of the IT load, and the investment rate of return is estimated to be 19% with a total payback period of 7 years. This technology will strengthen our team's commitment to green operations for sustainable computing.
In summary, a 1 megawatt data center in a 40-feet container, PUE less than 1.05, no fans, and that's a conceptual design with two-phase direct-to-chip to cold plates and immersion inside of a tray. So another product that we're working at NVIDIA is basically a research project with Department of Energy, ARPA-E, and that's the sort of thinking that we want the industry to think about. Think outside of the box. These racks are going to go higher densities. We need to have solutions, and we're working with all of you guys to achieve that solution. Thank you for your attention. Okay, sure.
Okay, we have 7 minutes for questions. Shall we start with one on Slack? And those of you, if you have questions, please line up in front of the microphones in the hallways, in the corridors.
Okay, thanks for your presentation. This one comes from Sissy Yuan from AI Chips. And she's approaching this cooling problem from a slightly different perspective. She's asking, is there a scheduler that assigns and maps tasks to the GPUs across the data center that's thermally aware so that the heat doesn't, cluster?
Very good question. That's part of our digital twin. We have digital twin builds for design, and we have digital twin builds for controls. So once we have this digital twin build, think about like a AI ChatGPT style. Build into the controls of the entire data center that can basically predict the workload. Workload of an AI workload is not like a CPU workload. It's a massive workload. Basically, you bring this huge workload, and this huge workload, not just one rack, a cluster of racks, could be multiple cluster pods, solve one problem, all of them become one GPU. It's a huge amount of swing in the power. So given the environment, given the ambient, given the workload, the idea that we are working throughout NVIDIA is through a controlled digital twin in operation project is to predict that and prepare for that. So once we predict it, then we can prepare both from the power distribution and the cooling units so that we know the workload is going to hit the racks. We're going to prepare, maybe make it cooler, make sure that the facility is able to take this swing in the power and go right through it. And that's part of the work that we are doing with the digital twin.
Thank you. Gentleman over there.
Yes. The idea of putting a data center in a shipping container was tried by Sun 10 or 15 years ago. What's changed now?
Very good question. I'm very proud to be part of the black box when I designed the black box at Sun. That was absolutely a good project, and a lot of HP and others have created containers. This ARPA-E basically had a very huge restrictions. You have to be able to create a 1 megawatt cooling. None of the 40-foot container. None of the projects that I know of is up to a megawatt with ability to get efficiency of 1.05, PU of 1.05, so very low efficiency and ability to maintain racks of up to 160 kilowatts per rack. That's extremely aggressive. When Department of Energy put that, I really strongly suggest look in the cooler chips. There are many universities and research institutions that are working, industry working. Nvidia is one of them. That's totally off the scale from anything that was done in the past.
Thank you.
Thank you.
Thank you. Please, go ahead.
Sarah Biabani, and so this is great. So you've shifted the design to digital twins, right? So
Yes.
the two-part question. So one is how, what's the fidelity of the digital twins? How well do they mimic the real world? And how reliable are they? And I know you have the compute power at Nvidia to do this. So it's okay. And then the other part is, in order for this whole ecosystem to work, you need to have models, digital twins of all the components, which you're not going to build yourself. So what kind of standardizations do you need, and what kind of interfaces would you like to standardize?
Very good question. Yes, absolutely. So fidelity of CFD is very well known. When we build data centers, we basically build data center with flow network modeling based on the fact that this entity that I built is going to go through commissioning. Commissioning is a step that I bring load banks, liquid air load banks, and test it out. And test the capability of a data center. So when I build the CFD, I test it with actual equipment with load bank and predict. Normally, I'm within 1 to 1.5 degrees C away from that. So we're not changing anything from the existing practice. We're basically porting everything into one platform. Rather than having separate entities, like CFD separate do CFD for air, ANSYS do mechanical, other two do electrical, and SketchUp do the design, we're putting all of them together, working with the entire industry, so all of this can be done at the same time. So you don't have to go out and do a CFD separate from an ANSYS mechanical design to see what happens if there's enough transfer, a seismic event versus an ambient, those are all put together. It is a tremendous, everybody's talking about digital twins, and it requires ecosystem, and we're working. So there's a huge team within NVIDIA that's working on digital twin, Omniverse, and they're creating, Jensen talks about Earth 2. I think Earth, if we can solve the Earth 2 problem, the air distribution and the simulation of the air movement around the Earth to the scale that can go down to such a small scales, we will be able to create the same thing for our data center. Standards are being built. We're working with the industry. There are tool sets that NVIDIA has created, but we need everybody's engagement. These talks is motivating in research institutions as well as industry, hopefully, to join us in this task.
Thank you.
Thank you.
Do we have another one from Slack?
We do.
Okay, great.
So this question was posed by Cliff Young, and I'm going to add a couple of my own questions to this. So he's asking, are there physics-based limits to how far we can get with liquid cooling? We're asking you, who's extremely experienced and has thought about this problem for a long time, do you see where the limit is? Or do you see what problems are going to be key limiters to our ability to cool the chips?
Sure. I think as like air cooling, in my opinion, the limit of single-phase liquid cooling is not going to be limits of physics. In other words, I can always do air cooling of chip a kilowatt and above with fans and heat sinks. It just becomes impractical in action. The same with liquid cooling. I don't think that I will have a whole lot of problem cooling chips up to several kilowatts with single phase. And the roadmap to where we need that amount of cooling has to be defined. We are not, I'm not a chip designer, I'm not a product, I produce data centers. But from my perspective, rack density and the rack basic cooling becomes a higher priority than chips. So if I go from air cooling, 40, 50 watts per centimeter squared on a chip, goes from air cooling to liquid cooling. So if I have a chip at 40 to 50 watts per centimeter squared, that's where the limit is from most of the stack up of packaging from the lid and thin material and the heatsink and what have you. When you go to about 200 watts per centimeter squared, when you have heats that are generated between the GPUs at 230 watts per centimeter squared, the transition from air cooling to liquid cooling will happen. Now, that's not a suggestion that we're going to have that level of chip density. But talking about physics, that's where I think the physics is going to bend, where we don't have enough liquid going through anything that's like a best-in-class cold plate, that's probably at 0.015 degrees C per watt, the typical best cold plate, that can maintain the case temperature on that GPU to that desired level. So imagine as the heat density goes up, so I can bring in 0 degrees C. It's going to be freezing. Normally we get like 17 degrees C just to stay above condensation in a data center. If I go to 17 degrees C, no matter how much liquid I can push through this 0.01 degrees C per watt cold plate, there's no way I can maintain its case temperature, in my opinion. And that is where the transition from single phase is going to happen. In my opinion, that's way out there. The transition may happen sooner because we will have more restrictions coming from rack density itself. And the rack is going to be defining and what do I mean by rack? Okay, typically we think about the liquid cooling at LPM per kilowatt. So 1 LPM per kilowatt, 1 liter per second per minute per kilowatt, okay? Now if that rack goes from 100 kilowatts to a megawatt, okay, how much water are you going to push into that rack? What's the size of the manifold? That is the restrictions. So the fluid flow, the limitation of how much liquid you can put inside of those racks becomes really difficult. And how you can manage that liquid delivery from cooling distribution units all the way to where it needs that amount of liquid. Even the chip can be low power, can be at around 60, 70, 100 watts per centimeter squared. But when the rack becomes 700 kilowatts rack, the amount of liquid delivery to rack becomes major issue.
Right, and that's fundamentally the question, because as we start to look at going 3D with chips, we're going to keep pushing higher power densities into a smaller space for you to deliver liquid to.
Yeah.
Hence the question. Okay, thank you.
And that's the limitation.
Very comprehensive answer. Thank you very much. We're out of time, but that gentleman's been waiting for a long time, so I'll let you ask the last question.
Yeah, thank you. It's Venkata Chipkula from Google. I would like to know, you mentioned few slides about erosion and what is done in terms of corrosion, etc., to improve the reliability. From your perspective, what are things that are driving reliability, and what is being done to improve the reliability for these new cooling solutions? And with the rack densification, and what do you see as a target for reliability?
Very good question. So reliability, I think everybody who has dealt with water knows its biogrowth is a major issue. You have to constantly manage that growth of bacteria. And one of the issues that we had started from 4 years ago, we're going to change the heat exchanger medium. We're going to change air to something else. We better have a consensus with the industry. So we had to do a lot of research. In our research, PG25, 25% propylene glycol, if it is run continuously, it has the lowest potential in terms of the biogrowth and settling. So I think when you have a PG25 continuously circulating within the loop, the maintenance requirement becomes minimized, and that kind of follows what I consider liquid cooling. Always thought about it is it's like high deliver power to the racks. I don't want anybody to see a single drop of liquid. You don't want to see an electron jump out of your cables. You don't want to see a single drop of liquid jump out of your tubes. You don't want to have to go and maintain your liquid line because you don't maintain your air lines. Your air coming in through your cryo units, we tried to mimic the existing practice. And so there are industrial standards. So I'm working with ASHRAE, American Society of Heating and Refrigeration, air conditioning. They're coming up with standards. Those who are interested, there's a meeting in Orlando in January this year. There will be a new specification coming out from ASHRAE. That's probably one of the most comprehensive ones coming out. OCP is doing this. Open Computer Project is doing the same thing. But there are ways that I think industry is converging, and we are coming up together very well to a solution that we think that reliability, we can maintain what existing practices with air cooling, and probably even better.
Thank you very much, Dr. Heydari.
Okay, thank you.
So that's the end of the session before the coffee break.